Hello everyone, in this lesson we're going to see how to optimize the volume and surface area of rectangular prisms and cylinders. Let's start first with rectangular prisms. To optimize the volume of a rectangular prism, if the surface area is fixed, we must make it a cube. Now we know that in a cube, the length, width and height have the same measurements. If we assign that measure with x, then we can write the formula for the surface area of the cube as 6x squared. Because cube has 6 faces, the area of each face is width multiplied by length, so x squared, since they are equal to each other. In that formula now, we can isolate x. And x equals square root of surface area divided by 6. The value of the x, we're going to take it and substitute it on the formula for the volume of the cube, which is x cubed. From where we get the volume of the cube, square root of surface area over 6, all to the exponent of 3. So that means that if the surface area is given to us, we can figure out what is the measurement of the cube, what is the side of the cube or the edge, and we can figure out what is the maximum of volume that we can get out of that given surface area. Keep in mind, we must make that rectangular prism a cube. The same thing will happen when we have the volume fixed and we need to figure out what is the least amount of surface area that we can have for that given volume. Again, we must make that rectangular prism a cube. But now the given information is the volume. So to figure out what is the measure of the cube, we're going to use the volume. We're going to isolate the side or the variable x, and that will be the third root of the volume. This information, we're going to use it in the formula to figure out what is the surface area of the cube, which is 6x squared. Instead of x, we're going to write the third root of the cube and figure out what is the minimum surface area when we have a fixed value. Let's look at one problem that we have here. A product must be shipped in a container in the shape of a rectangular prism made of cardboard. Given that a fixed surface area of 8 meters squared of cardboard is available, what is the maximum capacity or volume of the container? So what is given to us is the surface area, and we need to maximize the volume of the container, so we must make that a cube. Now we know that the surface area of a cube is 6x squared. As we saw before, isolating or figuring out what is the side of the x now. Divide both sides by 6 and then take the square root. You end up with the value of x equals to 1.2 meters. Now that we have the side of the cube, very easily we can figure out what is the volume, which will be the value, the maximum volume, and that is what we wanted. So the volume of the cube is x cubed. Substitute the value that we found for x from the given surface area, and this is the volume, the maximum volume, 1.7 meters cubed. So this was one example for how to maximize the value when we have a given surface area. Now on the second part, we're going to see how to optimize the volume or surface area of a cylinder. The rule that we're going to apply, or the rule that we're going to see, is that to optimize the volume of a cylinder, if the surface area is fixed, we're going to have to make the diameter equal to the height. Again, the same approach as we did with rectangular prisms, knowing that the diameter equals to the height, we're going to use this formula. So because the formulas for the surface area and volume of a cylinder are expressed in terms of the radius, instead of expressing the height in terms of diameter, we're going to have h equals to 2r, and we're going to substitute that into the formula for the surface area. because the surface area is what is given to us, so we have surface area fixed. From here, substituting instead of h to r, we're going to have a new surface area, a formula for the surface area, which will be 6 pi r squared. And we maintain that by substituting 2r instead of h, and you're going to have 2 pi r squared plus 2 pi r multiplied by 2r, which will give you the second term. Will end up into 4 pi r squared. Adding these two like terms, we're going to have surface area equals 6 pi r squared. From here, we're going to isolate r, as we've seen before. Divide first both sides by 6 pi, and then take the square root of both sides. Therefore, x equals surface area over pi. Now, with x, we're assigning the radius. So, radius is the square root of surface area over 6 pi. We're going to substitute that into the formula for the volume of the cylinder, which is pi r squared h. Again, substituting instead of h to r, the new formula for the cylinder will be 2 pi r cubed. Since we figured out what is the value of r, we sign it with x up here. The new formula for the volume will be 2 pi square root of surface area over 6 pi all cubed. Okay, let's see an example now. Suppose we are designing a can with a volume 300 milliliters, and we know that 1 milliliter equals to 1 centimeter cubed. Determine the radius and the height of the can if you wish to optimize its surface area. What is the minimum optimum surface area of the can? So what we have here is the volume. The volume is fixed, and we need to figure out what is the minimum surface area that we can create. We can use to create a cylinder with this volume. So we know that we have to make diameter equals to the height, or height equals to 2 radius. That means that the formula for the volume, pi r squared h, will be written as pi r squared multiplied by 2r, as we saw above, 2 pi r cubed. Now here we're going to isolate, we're going to figure out what is the radius. We have the volume 300. Substitute that into that formula, and we're left with only one variable r, and isolating by dividing first by 2 pi both sides, and then taking the third root on both sides, we end up with a radius 3.6 centimeters. Now that we have the radius, we can figure out what is the height. The height is 2 radiuses, right? So the height of this cylinder will be 7.2 centimeters. Now that we have this, we can figure out what is the surface area. So plotting everything into the formula for the surface area, we figure out that, so in this example here, we have substituted the value of radius and the value of height. And we come up with a minimum surface area of 244.2 centimeters squared in order to have a maximum value of 300 milliliters or centimeters cubed. Hope this is helpful.